Doing well, how are you?
Doing fine.
Awesome.
I have my last semester of college starting next week, so
Nice. Cool.
trying to get in as much
Mm-hmm.
studying until the everything else starts.
Mm-hmm.
But yeah.
Got it.
So today I wanted to go over some AAMC stuff.
Okay.
Um, it's from the official guide.
Okay.
It's like these questions. Yeah.
Okay.
Are you able to see them?
Mm-hmm.
Okay, good. Okay. So I can start reading and then I'll just tell you if I see buzzwords and we'll go from there, right?
Okay.
Okay. Um, Trinitrobenzene sulfonic acid is a membrane impermeable reagent that combines with phosphatidyl ethyl whatever P as shown in reaction 1. Upon reaction, TNBS labeled P molecules are frozen on the outer envelope of membranes and do not exchange with other P molecules on the inner envelope.
When they say membrane impermeable,
Uh,
what do they mean?
they mean that they're basically hinting at the fact that these molecules are hydrophilic. They're polar.
Good.
So yeah, that's what I'm thinking when I read that. So maybe, as you say, they might be asking amino acid questions.
Mm-hmm.
What's hydrophobic, whatever. What's hydrophilic?
Yep.
Okay.
So we have our reaction one here, so they're giving us the structures. So whenever you see that, you want to look for functional groups, for instance. So like this thing on the left, what do you see?
Um, I mean, I see like carbonyl. It's an ester.
Okay.
It has
Show me, yeah.
hold on. So they call it an it's I mean it's an amine, apparently. So, well, yeah, there's the NH3 plus.
Okay, so that's the amine group. What other groups? You said there was esters.
Well, right here,
Yeah.
yeah, that's an ester group, right?
Yep. Is there any others?
Um, well, phosphate.
I mean, just another ester. Is there another ester?
Oh, is there another ester? Yeah, right there. Like, I don't know if you can see my
Okay,
cursor.
good. So now, what do you think this molecule in the middle is from?
What the molecule in the middle being what?
Uh-huh.
This one?
Nope.
The phosphate? Oh, I mean, it's probably from glycerol.
Glycerol, right?
Yeah.
Good. And then this is when it forms a like bond with the fatty acid, right?
Mm-hmm.
Here's another one.
Yeah.
And this is our phosphate.
Mm-hmm.
So if we didn't have this, what would this molecule be an example of?
Of a phospholipid.
Phospholipid, right? And now that we have that, we just, what are we adding?
We're adding an amine. So is this what you call the phosphatidylcholine?
Well, so there's an amine there, but there's also,
The phosphate?
well, what's in between?
Like a carbon?
How many?
One, two,
So
two.
that'll be what group?
Uh, I don't know. I'm like lagging. I mean,
Ethanolamine.
ethanolamine. Okay,
So we have
gotcha.
the ethanol, or rather the eth part here with the two carbons and the amine part there, right?
Hmm.
Um, yeah, now to, I guess, answer your question. This is very similar to a choline, except the choline is not going to be like, so if it was choline, it'll be like nitrogen and like three methyl groups attached
Hmm.
rather than ethyl group and then amine like this.
Got it.
Mhm.
Okay.
Good. So okay, you recognize those functional groups. Now, um, which molecule is this over here, the TNBS?
P.
What's up?
That's P.
Okay. Where's the TNBS?
Um, this one.
Mm-hmm. And so you can see that it's got a sulfonic acid aspect to it and the trinitro, three nitro groups,
Hmm.
and the benzene in the middle.
Yeah.
Hence trinitro uh benzene.
Hmm.
So do you remember what toluene looked like?
I think I literally did a question on that today,
Hmm.
but I mean, it's probably an aromatic ring. Like,
Yeah, it's a benzene with a methyl.
got it. Okay.
So let's say we had, instead of this sulfonyl group, you had a methyl, then what do you think this would be called?
Trinitrotoluene.
All right. And if you had to like abbreviate it,
TNT.
there you go. That's what TNT is.
Shane, you never fail to surprise me. That's a good one. Wow. Yeah.
Well, even more surprising is if there's a huge oil spill with or oil fire, what they can do to put it out is use like TNT or dynamite.
Hmm.
That's a little weird, right? Like why use that to put out a fire? What do you think?
I mean, I know that there's a lot of like oxygens on it,
Oxygen's on what?
the trinitrotoluene.
Oh, so I guess I'm saying like I'm like kind of like not talking about the structure anymore, but just
Oh,
something like TNT or dynamite, something like that. Um, like why would that be used to put out
like why they use TNT to eliminate oil?
like an oil fire to put out a fire like that? So it's the same reason, it's the same thing that you essentially do when you like blow a candle out. So there's a difference between a conflagration and a detonation. Conflagration is when something, like in terms of like, I guess blowing up, like produces fire. But detonation, detonate, I think I spelled it wrong, whatever. Detonation is more so the fact that it creates supersonic waves, pressure waves. When you detonate something, it's less so the fire and more so the supersonic waves that are created. So when you detonate something like a fire, um, you're basically like blowing it out like you would a candle.
Mm-hmm.
Hmm.
Okay.
Oh, and then also when something's burning, causing like a whatever, like yeah, when something's burning, it's a combustion reaction, so that requires oxygen. So you could also, so if you blow out your candle and stuff, you're essentially getting rid of the oxygen in that area. But anyway, cool. So it seems like, all right, we add this to the PE, and then it seems like it adds on to uh the amine, right?
Yeah.
And the sulfuric acid uh is also added. Is it also added, or is that that's a subtraction sign? So I guess yeah, we're removing it, so we no longer have the sulfonyl group, so it's just attached to it. Okay, cool.
Okay. Growing bacteria are treated with radioactive phosphate labeled phosphate. Okay, P32 labeled phosphate. Uh, Phosphorus labeled phosphate in an effort to identify the location of P synthesis.
Mhm.
Okay. In this
Labeling,
experiment,
yeah.
they label down. And in this experiment, newly synthesized P will contain the label. When growing bacteria are treated with a pulse of radioactive phosphate, followed by immediate treatment with TNBS. Almost none of the TNBS labeled P contained phosphorus. In contrast, if an interval of only 3 minutes was allowed to elapse between the phosphate pulse and TNBS treatment, almost 50% of the P labeled PE was also TNBS labeled.
Uh,
These results are
oh, sorry. Yeah, I'm trying to make sense of this. So growing bacteria with radioactive phosphate uh, shows in the newly synthesized PE that there's a label, but when you treat it with the pulse of radioactive phosphate, um, followed by immediate treatment with TNBS, almost none of the TNBS labeled PE contained the radio-labeled phosphate. I wonder why, but okay. All right. And then I guess you're up to like, in contrast, if an interval of only 3 minutes was allowed to elapse between the pulse and the treatment, almost 50% was also labeled. So, okay. I guess they give us a picture here. So, yeah, what do you see in this picture?
they're just illustrating like what they were talking about. So first you
Yeah,
put
so
in the
start with the caption.
summary of experiments designed to establish the location of lipid biosynthesis in a bacterial membrane.
Okay.
Okay, label unlabeled phosphate, it has no
Yep.
shading, labeled phosphate, and then TMBS.
So let's see. So we have our regular whatever lipid thing, and we add, we incubate with radioactive phosphate. So now some of the phosphates that seem to be on the inner side get radio labeled. Immediate incubation with TNBS. So now we see that we're adding the radio labeled, wait, we're adding TNBS. TNBS molecule is, I guess, what, the smaller circle?
Yeah,
You
like
can,
on the outside.
got it. Okay, okay, yes, then all of the ones on the outside. Okay. And then 3 minutes later. Oh, sorry. So this is when you immediately uh this part, the
Mhm.
pulse, and then immediately treatment with TNBS. Whereas this is when you waited the 3 minutes between the uh phosphate that you add and the incubation with TNBS that you do.
Mhm.
And it seems like when you wait, you have it seems like I see. So do you remember like flip ace and flop aces and all that?
Hmm.
So like there's more if you give it time, there's chances for it to like for the inner labeled thing to move to the outer level,
Hmm.
right? Whereas if you did it immediately, you're only going to get, you know, uh, it's only going to be the so I guess the thing is that once you add TNBS, it will start to, add to the molecule. So if you did it really quickly, it's just being added to the outside. Well, I guess in both cases it's only added to the outside, but if you do it immediately and it's added to the outside, it's added to the unlabeled phosphate, right?
Hmm.
Whereas here, you give it some time, 3 minutes, for some of the labeled phosphate to be on the outside as well, so that when we incubate with TNBS, like 50% of the of that TNBS can attach to the labeled phosphates. Yeah. That makes sense?
Hmm. Hmm.
Okay, cool. Okay.
Scientists who developed the experimental protocol described in the passage chose TNBS over many potential candidates to label PE molecules. What characteristic about the rate of reaction between TNBS and outer envelope PE molecules allowed the experiment to provide useful data? The rate of TNBS reaction with the outer envelope PE is faster than the rate of exchange between inner and outer envelope PE molecules. Slower than the rate of phosphate transfer across the membrane.
Let's think about this a sec. Like, what are they asking us?
Like what basically why did they choose TNBS
Mm-hmm.
and what about it reacting with the PE?
Uh-huh.
Um
Yeah.
basic
So they're asking why, there's lots of things you can use, right, to label PE molecules. Why use TNBS, right? And it seems like the TNBS enables us to have a difference whether we do it immediately after we incubate the thing with radioactive phosphate or if we wait, right?
hmm
So, and they're saying the rate of the TNBS reaction with the outer envelope PE molecules, right? So the if you don't wait, right, it doesn't really bind to any of the outer, well, sorry. If you don't wait, it'll bind to just the outer parts of the outer envelope, right? But if you wait, it will enable there to be, some flipping and flopping and whatever. So you can then, yeah. So okay, that's gonna play a role. So yeah, what are your thoughts here?
I'd eliminate C and D because easily measured by initial rates, like it's not, I don't think it can be measured because initial rates, like not, it doesn't react with, it doesn't react with anything, like any of the significant one, the
Uh,
shaded ones.
Yeah, so even though we're given a reaction, we don't talk at all about kinetics because kinetics have to do with rates of reactions, right? Right.
Hmm.
So we don't talk about rates. So D is out. C is saying facilitated by the additional phosphate present in solution. What are your thoughts?
Well, I crossed it out. I don't think it's correct because, I mean, like, they didn't talk about any, like, the main focus here is the radio-labeled phosphate, and like maybe it could be facilitated by additional like I just don't. I think it's a little out of scope.
Well, let's see. So if it's saying that it's facilitated by the additional phosphate, it means that the additional phosphate helps the rate of this reaction to proceed, right?
We didn't talk about rates.
Oh, but let's say that, if we didn't have that as a reason, right? Because ultimately we are still answering a question about rate,
True.
right? But facilitated would mean that it would enhance the rate of this TNBS reaction, right?
Hmm.
But the phosphate, all that does is it labels, you know, the uh what is it called? The PE. It just labels it. It doesn't change anything, in terms of rate. But yeah, so now I guess between A and B.
So the rate of TNBS reaction, um, it's a really fast, like basically, um,
Mhm.
hold on. Like I would lean A because like if when we immediately incubate it with TNBS, it right away reacts with the outer phosphate, and it's faster than the rate of exchange between the inner and outer envelope P molecules. Like here it said 3 minutes, and after 3 minutes, some of them flipped.
Yeah.
Um, I'm trying to understand why B would be wrong though. So the rate of TNBS is slower. I mean, I guess that's like the opposite kind of what this is saying, or I don't know.
Um, okay. So uh slower than the rate of phosphate. So I think that this question is trying to trick you in a way because like so okay, so we clearly observe like radio labeled phosphates that start off on the inner membrane can be on the outer membrane too.
Hmm.
So people might think, I mean, there's only two possible ways this could have happened. Either this like labeled phosphate can pass through the membrane to be on the outer membrane, right? Or the phosphate doesn't have anything to do with it, but it naturally flips and flops and stuff,
Hmm.
right? So B is saying the rate of TNBS reaction with the outer envelope PE molecules is slower than the rate of phosphate transport across the membrane. We should not have like that's if you think that that's how you get the phosphate, the labeled stuff on the outside. But we shouldn't have phosphates being able to travel or transport across the membrane because it's it's a charged molecule and it's not therefore it's uh lipophobic,
Yeah.
right? So yeah, so the question that they're really asking here is like so the observation is that from you know the so the sorry the radio labeled one can somehow reach the outer membrane. And there's only two ways that could happen. Either the phosphate travels through, or the molecule itself flips.
Mhm.
And we know that it can't be the phosphate going through because the phosphate is, hydrophilic. It can't go through the hydrophobic part of the membrane. So B is out. And A is comparing it to the rate of exchange between inner and outer envelope molecules. And that's pretty much it. So yeah, so that rate of reaction's faster because we only see them flipping and flopping when we wait, the 3 minutes.
Mhm.
Okay. Oh, yeah, yeah, you got this. This is also connecting like why the previous question couldn't have been, you know, beat.
Yeah. Um,
Yeah. And I guess when you saw this, that also kind of clued you in.
right.
Right? They're gonna ask stuff like that.
Okay, so
Now it's like what we said about so like again, when we looked at this, remember I was asking, what this group is?
yeah.
What did you say it was?
Fatty acid.
Yeah.
Um, I would think that it's C.
Okay.
Wait, hold on. Yeah.
So okay, so we definitely know that it's not going to be the this, right?
Okay.
And so then we have either one carbon, a carbon chain, and what's this?
Um, like, is it like this? I
Let's see.
don't even know.
You CH2 oxygen, it should be that, right? CH2 oxygen, right? C can make four bonds. H, that has room for two more bonds, but we only have an oxygen, so it must be a double bonded oxygen.
Well, yeah, it's not possible
Okay. Why?
because the acid's attached to the
Mhm.
like carbon.
Yeah. And, this means that there's 10 of these oxygens, right?
Uh-huh.
It's like, keeps going like that, right? So good. And yeah, and we also sort of foresaw this when we looked at, the molecule, we thought fatty acids. Yeah.
And waxes, um, I've read that waxes appeared on the exam before,
Uh-huh.
the like actual MCAT.
Uh-huh.
Just to make sure, are they like the same thing as fatty acids, but it's literally like what we just discussed, but they have like an OH at the end?
Uh yeah, so I have a uh shared drive document in which I go over it.
Okay.
Yeah, let me see if I can I'm gonna screenshot it and put it in the chat. You could open that up. Yeah, I have a couple of pages of lipid notes. Okay. Yeah, so let's go. So the top I wrote, okay, lipids. These include fats, fat soluble vitamins like A, D, E, K, uh, some hormones, sterols, steroid alcohols, waxes, which are esters with long chain fatty acids, combined with long chain alcohol, fatty acid esters of glycerol, like monoglycerides and phospholipids. So you have a phospholipid drawing, a wax drawing, um, steroid drawing, progesterone in particular, vitamin E drawing. And if you scroll down, I go
How's
into
that a wax though?
what's up?
Like, how's this a wax?
Oh, is it not? Let me see.
No, no, no. Yeah, I mean, I don't know. I'm just wondering
Oh, so
because this looks similar to the fatty acid, you know?
yeah, but it has two oxygens, right? It has the ester within it. Um,
Okay.
Like, oh, I thought you were talking about this one.
Hmm?
Sorry, I thought you were talking about this one. But
Oh, so I'm talking about the wax drawing here.
yep.
Like, how is this different from um this right here?
I see. So, um, so yeah, you can um scroll down a bit.
Okay.
So waxes, I wrote. Oh, I guess it's cut off.
Yeah.
Well, yeah. Okay. So highly hydrophobic, high melting point, highly malleable solids. So we have these examples of waxes where you have a large carbon chain to the left and right with an ester in the middle,
Mhm.
right?
Mhm.
But that's so yeah, so that's R like that, right? So you
Mhm.
don't have a glycerol backbone in this,
Oh, okay.
right?
Got it.
Mhm.
Okay, this label generated from naturally occurring I mean, I got this right. It's an isotope. So phosphorus is normally 31 mass number. Atomic number is 15. So yeah, can't can't add a proton because it's gonna change it to a sulfur. Adding 3 electrons is gonna make it an ion, and then it's between these two, and it's D because
So you said
mass number goes up.
you wouldn't be it because it would turn into an ion. Um, Tell me more. Like what? I mean, could there be another reason?
Uh,
Like why electrons being added wouldn't work? Well, it's because we're changing the mass, right? And electrons don't have masses.
oh yeah.
Yep.
Uh-huh.
Mhm.
Yes. Okay. Yeah, this was a toughie, at least from when I did it the first time. Got it wrong. So
Mhm.
one of the experimental questions. These are at this point in my studying, I get these wrong the most out of anything.
Uh,
So
Experimental design.
yes, I like
Yeah. Okay.
most of my mistakes, unless they're a stupid mistake, like really dumb, just not reading. Like
Yep.
this is yeah. So yeah. A scientist proposed that the 32P label was entering PE molecules by direct exchange, swapping phosphate groups with those found in solution, and not through the synthesis of new PE by bacterial cells. Whether experimental modification can show this is not the case.
Um, Scientists proposed that the P32 label was entering PE molecules by direct exchange, swapping phosphate groups with those found in solution, and not through synthesis of new PE by bacterial cells. And what experimental modification can show that this is not the case? Not, not double negative. So I guess they're asking which modification can show that you are having synthesis of new PE by bacterial cells. or something that shows that they're not entering by direct exchange, right?
Yeah.
Okay.
Well, if you want to show that they're doing it through bacterial cells, you can remove C.
Tell me, uh, oh, I guess you're saying like if you get rid of the bacterial cells and you use a mouse cell culture that,
Actually, I mean, yeah, it could actually work.
so let me see here. So we want to show either that, you know, is not through direct exchange or that it is synthesized by whatever bacteria. So if we use mouse cell cultures instead of bacterial cells, that would show that it can't be synthesized by bacterial cells, right? But we want to show that it is synthesized by bacterial cells, right?
Hmm.
So if we didn't have bacterial cells, we can't show that, right?
Hmm.
Okay. Um, and then let's see, decrease the concentration of the phosphate to observe the effect of in on incorporation rate. Um,
Close up.
so I mean, the rate would depend on the enzyme, wouldn't it? Like you could change the concentration to cause some type of like, Le Chatelier principle thing, but uh which will tell you if it's moving forwards or backwards, but the rate itself is determined by, you know, the catalyst, the activation energy, and that's what the enzymes do. So, so if we wanted to see the effect on incorporation rate, we would have to change like, um the enzyme, right? So now A says introduce TNBS before pulsing with the phosphate. Um, that would cause the TNBS to, I guess, attach onto the outer membrane. Um, and then if you add the phosphate after, it would, you know,
Repeat it again, sorry, because I was writing down the reasons why C and D are wrong.
oh yeah. So, so okay, the phosphate is what labels it, and the
Hmm.
TNBS is what I guess, yeah, incorporates itself into like, that outer shell, outer envelope.
Right.
And let's see. Um, yeah, so okay, if you did the TNBS before pulsing it, you'll have the outer uh membrane um, you know, be attached to the TNBS, but you won't have the phosphates labeling
Right.
anything. But if you measure the rate of incorporation into A-cellular PE, right, then you can see if you are able to you like have it be a direct movement of the phosphate, or if it's something that's being synthesized. So if it's an acellular PE, that means that, well, it can't be a bacteria, it can't be any living creature. Um, and let's see. And I guess you should see like a smaller amount perhaps because, acellular PE is if that was labeled, that would, I guess, support the case that it's through direct exchange rather than the synthesis. So,
But what about it being incorporated in something acellular? Like, how is that?
so I think that, yeah. All right, the rates of bacterial PE synthesis and any potential phosphate exchange should be different. Also, it's unlikely that a phosphate would exchange from a phospholipid. Acellular PE, which is PE without, that is not associated with a cell, wouldn't be able to synthesize new PE. Okay. If we saw P incorporation with acellular PE, this would support the direct exchange. And if not, we'd have evidence against the direct exchange. So the way that I wrote it, um, like P not direct and P is synthesized bacterially. I guess honestly, this could go the other way around too, because they're just saying, how can we tell that this is not the case, right? So yeah, I think that also includes because what we're doing here is we're in an acellular like environment. It means that this can't happen. Like it can't be synthesized from bacteria. So whatever change in rate of incorporation of the radioactive phosphate would tell you that it's happening directly, I guess.
Mhm.
Yeah. So yeah, so now like a zoomed out view would be, are like how can we tell if we're adding phosphates directly or that bacteria is synthesizing the phosphate? And if you use acellular, like non-cell environment, and you get phosphate incorporated into stuff, into the PE, that must be through direct means because
Makes
there's
sense.
no living cell. Yeah.
Honestly,
Mhm.
what the main thing is I didn't know what acellular really meant. And so that I guess that's the main reason why I got this wrong. But
Whenever
yeah,
an A in front of a word,
it's yeah, opposite.
Mhm. or
Yeah,
less so opposite, more so just not.
got it.
So, I uh
Mm,
there's like in psych, there's like, antisocial personality disorder,
okay.
right? Like, know about that?
Yeah.
Tell me about it.
Well, I feel like I know what you're gonna say, but most people think antisocial
Yeah,
is
yeah, exactly what I was saying.
like an introvert, but
Yeah, yeah,
antisocial actually means you're just actually like against society and want to
yeah,
like
yeah. So
yeah.
people usually say antisocial, they should really mean asocial.
Yep.
But yeah, you know exactly what I was gonna ask.
Hmm.
And yeah, antisocial personality disorder, that's like for like psychopaths.
Right. Yeah.
Okay.
Quickly though, if I make an Anki card for this, because I just want to make sure, like, what would you put in? I mean, like, I guess just ace. Main thing is acellular here,
Um,
or
let's say, okay, let me write some stuff down. So we could say that, um, Okay, I wrote that PE is labeled by isotopic phosphorus through either A, direct exchange, in which it literally just swaps on an unlabeled phosphorus on the PE with labeled phosphorus in the solution. So like if you had like P32 label here, like on this phosphate that's in solution, it can like this can leave and then this can come in and take its place. That would be a direct exchange. Um, or it could be B, that the bacteria is synthesizing the PE, also using labeled phosphorus from the solution, right? But you know, that's the main difference. So, oh yeah, then let me put in so um if you use A-Cellular PE and you see that it is labeled with, P32, it must mean that this happened, or rather, it must mean that this, or rather, it cannot be from bacteria and must be direct exchange. Putting that down here. Yeah. So there's two ways that phosphorus, isotopic phosphorus, can enter into the PE molecule. Um, Either direct exchange, which is just swapping the unlabeled phosphorus on PE with the labeled phosphorus in the solution. That's one way. Another way is bacteria can synthesize the PE also using phosphorus from a solution. So if we just had radiolabeled phosphorus, we would not be able to tell if it's happening through direct exchange or the bacteria making it. However, if you use acellular PE, that means it's not a living thing. And, let's see the results. And if your results show that you have, the radiolabeled phosphorus in your PE, it means that it cannot be from bacteria and must therefore be direct exchange.
Yeah.
So the things that I wrote, did you?
Yes.
Okay.
All right. Hard water contains cations that form precipitates with soap or upon boiling. The principal hardness ions are Ca2 plus, Mg2 plus, Fe2 plus. There are two major drawbacks of hard water. First, the M2 plus ions reduce the effectiveness of common soaps, which contain the sodium salts of organic acids with long carbon chains. So I think soaps is a buzzword.
Wait, let me see.
Uh,
So let me just read this. Hard water contains cations that form precipitates with soap or upon boiling. The principal hardness ions are these. There's two major drawbacks of hard water. First drawback is that the plus two cations reduce the effectiveness of common soaps. Um, and okay, yeah, you said soaps buzzword. What can you tell me about soaps?
Basically, when you have like a fatty acid and an NaOH comes, um it can knock off the fatty acids that are bonded to the glycerol. And I honestly don't even know what exactly is the soap part of it, but like I know that's the whole thing.
So let's see, right? So why? So okay, like why not just use water? Like if you take a shower and you just use water, why isn't that going to be enough?
The water is just gonna take like a hydrogen. It's not
Um,
gonna break it.
so the thing is that So water can dissolve things that are hydrophilic, but the oils on, your skin and your hair and stuff, uh, that kind of stuff is hydrophobic, right?
Yeah.
So a soap has a hydrophobic long carbon chain region that can solubilize the fats, the oils and stuff, but it also has a charged end, which makes it hydrophilic. So when you lather, yourself with soap,
Hmm.
the fats, the oils and grease and all that stuff get kind of solubilized or attached to the hydrophobic part of the soap. And when you then use water, the water solubilizes and it attaches to the charged part of the soap, and you get that out.
Hmm.
Okay. So
Yeah.
yeah, so they say that there's sodium salts. That means that there's going to be a charged end, and then long carbon chain is your hydrophobic part, right?
Yeah.
Mm-hmm. So okay, so now I'm gonna just write that like M2 plus is inversely proportional to like soap, effective effect. Um uh okay. And it could make sense because it will form precipitates with soap. Maybe, turning it into like a solid when you want it to be, you know, uh having like a positive or a negative end. So okay. An example is sodium stearate. So there's that. Um, so like, this means that, in solution, the sodium dissociates, and this will just be a negative charge then, right?
Hmm.
And that'll be the part that's water soluble. Okay. The reaction between soaps and hardness ions yields insoluble precipitates through reaction one. Reaction between soaps and hardness ions gives you okay. So we know that it forms precipitates with soap, and now we have the reaction here. So we have our M2 plus cation, we have our sodium stearate, I guess. Um, and then it dissociates into the sodium ions, and this would typically have a 2 minus charge, right? But now it's going to like form a bond with the M2 plus to give you this, and that precipitates it,
Okay.
meaning like turns it into a solid.
Yeah, and so that's why it's reduced. The effectiveness is reduced.
Yep. Because to get soap to work in the first place, you need to, mix it up with water, right? You can't just take a bar of soap and just dryly go like
Yeah.
so. Okay, and then they say removal of the stearate from the solution eliminates the effectiveness of the soap, and that's what they're doing by precipitating it out. Like this form you want it to be in, but when it's precipitated, it doesn't, it's no longer effective. So I'll say proportional to precipitation, um, of soap, and that means it's less effective.
Hmm.
All right. Um, Then they said, okay, so like they mentioned soap or boiling. So now I guess we're talking about boiling. So hard water produces boiler scale, a layer of insoluble carbonates. Insoluble means what?
It can be soluble, I guess in this context in water.
So wait, you said so what does that mean?
Insoluble.
Mhm.
It's not soluble in water.
Uh-huh. So that could just mean it's forming a like it's forming a solid, right?
Okay. Yeah.
right? Because I mean, if something's soluble, it can mix in with whatever water, right? If it's unsoluble, it's not going to mix and it'll retain, if its solid structure, right?
Hmm.
So reaction two that lines the inner walls of pipes and hot water boilers so that the pipes
Wait, so are only liquids and aqueous things like soluble in whatever?
um
Because like
well
I know nonpolar is most soluble in nonpolar stuff. Like hexane is very soluble in hexane. While like and then, something that's polar like phosphate is the most soluble in something that's polar like water, right?
yeah. So you'll have like dissolves like always. Um, but if you imagine like a KSP value, like let's say it's like 1E, I don't know, -7 or something like that, that's the maximum concentration for which at which this thing is soluble. If your concentration is higher than this KSP value, you're gonna get precipitation.
Okay, so we have to factor in KSP as well.
I mean, like that's just to kind of show you something like what KSP means. It doesn't mean that we have to do KSP for everything that we see that is soluble or insoluble. But the idea basically is that like, let's say that you have something soluble in water like salt, right? Like regular table salt. Um and you put some of that salt into water, you get your sodium ion, your chloride ion. Now imagine adding like a pound of salt to like uh, a little cup of water. The water will solubilize as much of it as it can, but there's just so much salt that the rest of it won't be soluble and it'll maintain its solid form.
Hmm.
Okay. So
Okay.
yeah. Um, okay. So like, okay, reaction two. So we have our, 2 plus cation for our hardness. We're adding um bicarbonate and we end up with this solid here. Um, and that lines the inner walls of the pipe, so that's why the radii of the pipe can decrease. Um, and I have a feeling they're gonna ask us something like about the continuity equation
Hmm.
because they said the pipe's radii goes down, so that's like the area going down, so
Yeah,
the
they will.
go up. So that's, another buzzword here. Um, okay, deposits of this type are especially bad in hot water, um, and are poor conductors of heat. So, okay, then whatever. It's important that the cations responsible for hard water be removed before the water is heated or used for washing. Water softening, the removal of hardness ions from water can be accomplished in several ways. One method is the ion exchange process, in which water is passed through a column containing solid sodium aluminosilicates. Um, these are high surface area three-dimensional extended solids with ONA groups on the surface. So yeah, they'll ask you something about chromatography likely. And reaction three shows, I guess the sodium aluminosilicate solid and the, hardness cation, and it causes the hardness cation to bind to the sodium aluminosilicate, and it'll kick off the sodium ion out. So okay, cool.
The hardest ions described in the passage are alkaline earth metals.
Yeah, the second column, yeah.
Yeah.
Yep.
But um they're not because Fe is a transition metal.
What wait.
Fe2 plus, right?
Oh crap, I didn't even realize that. All right, yeah, yeah, you're right, you're right. Okay.
Yep. Strongly acidic cations.
Oh, I see. Okay.
So strongly acidic, I feel like something that's acidic has it's either very like it either has like hydrogens it could donate
Mm-hmm.
or because acids donate H's. And also like yeah. Uh,
Hmm.
why would this be wrong? Like I mean I'm pretty sure it's wrong, but
Yeah, yeah. Well, yeah, these cations are not really acidic or anything. You could have um well, I know like yeah, yeah, okay. So yeah, there's nothing here that is showing that these cations are, behaving as acids because they're not, you know, donating protons or anything like that. So, yeah.
formed in nature by reduction of other cations. Reduction is gaining electrons. So like when you're gaining cat other cations are gaining electrons. Seems weird.
Yeah, I think they mean like if you had like something with 3 plus and it gains an electron, it'd be 2 plus.
Hmm.
But that's yeah. The one thing, yeah, so yeah. The one thing that yeah, go on to the next one. Yeah, that's something that is absolutely true because yeah, that's what gives them a +2 charge.
Yeah.
Oh, apparently, okay, small, highly charged cations like Al3 plus are strongly acidic. Okay.
I'll write that down.
Hmm. Maybe that has something to do with, well, maybe not. All right, got it. If you have, once you get to 3 plus, you're in acidic territory. So Fe 3 plus is, acidic. Um, yeah, Al 3 plus. So I guess small, highly charged metal cations. Um, yeah.
Interesting. Um, yeah, I don't know. I mean, like, it's like a Lewis acid sort of hemoglobin thing, but even in hemoglobin, it's Fe2 plus.
I think it changes, right, from Fe3 plus to Fe2 plus or something. Uh,
Yeah,
but I think
yeah,
that has more to do with the size of it to fit in. But yeah, here, yeah. So we just know now that if it's beyond, if it's 3 plus or beyond, uh, like a cation that's 3 plus or beyond, that they can behave as acids, perhaps. Yeah.
yeah. What happens to the pH of a soapy solution as a result of the introduction of hardness ions? It's probably alluding to reaction one. Um, what happens to the pH? So I would think nothing.
Wait, which reaction are you looking at?
So I mean, I guess it could be any of them. I
Hmm,
thought it was the first one at first, but they're just saying introduction of hardness ions. So,
it'd be the first one because the second one is talking about hard water. Sorry,
oh,
the boiling. right?
Got it. Okay.
The first one's talking about the soaps, so we're gonna look at this.
Mhm. Yeah, I mean, I would think that it's not changing because I guess there's like re redox reactions. I don't really know.
pH of a soapy solution as a result of the introduction of hardness ions. All these questions are about pH, okay? Um, so pH increases as H plus increases is impossible, right?
Yeah.
pH is not changed. The pH depends only on the identity of M2 plus. That shouldn't matter, right? Like, as long as it's 2 plus, right?
hmm
Like, it doesn't matter if it's this, this, or this.
hmm
So, okay, that's out. So now either it doesn't change or it decreases as OH minus decrease. Okay, yeah. If OH minus decreases, H plus increases, and pH decreases. So B and C are both like internally that like consistent, but now okay, introduction of hardness ions. Um, hmm, solution. Insoluble precipitate. pH. Removes the effectiveness of soaps. Okay, I think that so this dissociates into 2 minus ion, and
Okay.
if it let's see, the 2 minus ion would be like uh basic a bit, a little basic, so it can take hydrogens from the environment, causing the pH to increase. And if the M2 plus ions, the hardness ions, like don't let this stay negatively charged, like it will donate the 2 plus charge to give you this. That means that you are not taking hydrogens from the environment anymore, so they're present, and that means that the pH should decrease then, right?
I'm confused.
Yeah, so we have like Na, like the C17H32CO2. So once we put this in water, it will dissociate like this. Well, there's a two there, so it's really two of these, and C17H32 CO2 2 minus, right?
Yeah.
Now this would act as a base, right?
hmm
because it has a negative charge. So like from water, right? It can protonate itself uh from the water. Um, or rather, let's say that we have H pluses in solution. It will take those H pluses, right? Causing a decrease in the amount of H plus, which would mean an increase in pH, right? Normally.
Yep.
But now if we're using the hardness thing, it doesn't let this stay negatively charged. Like your M2 plus comes in and, binds to it, eliminating its negative charge. So now the protons are not getting taken up by the base anymore. So you end up with more protons, which means the pH decreases and the OH minus must also decrease.
Okay.
Yeah. Ah, yeah, yeah, yeah. Mhm. Yep. The conjugate bases.
Sure. Basically, if you remove the function of 2 Na C17H32 CO2 plus, it cannot dissolve into ions and therefore it cannot react as a base with water and okay. So soaps are chemically modified natural products that can be derived from all of the following except
Hmm.
phosphorus just have a they have a different structure, yeah.
Yeah, they have that four carbon ring, but we're really trying to answer the fact that soaps are from fats, and that's fat. This is a type of fat. Fatty acids are a part of fats as well.
Mhm. Yep.
Oh, okay. All right. Well, I guess now they're talking. So, like, it's a Poiseuille's law one now, rather than a simple uh continuity equation thing, but shouldn't be too different. Um, okay, a pump is used to force an aqueous solution through a pipe at high temperature. Delta P is the pressure difference applied by the pump. R is the radius of the pump, and which we know is decreasing, I think. But let's see. L is the length. All right. Depicts the rate of energy consumed over time to maintain constant flow in this pipe through a pipe subject to the boiler scale. So the energy part, energy rate of energy consumed. How can I get energy in here? Um, well, okay. So we know that our radius is going to, over time, will decrease. And I still don't know, like, all right, rate of energy consumed. Um, Rate of energy. I don't know what to like, what that even, how to connect that. Um, oh, there's PV work, right? I'm trying to
Mhm.
find ways to find energy from Poiseuille's equation. Um, and I know there's PV work.
Mhm.
Okay. Oh, well, okay. That means that work is proportional to pressure. Maybe you can say it's proportional to delta pressure. Um, and radius is going to be inversely proportional to that change in pressure, right?
Mhm.
So
Mhm.
the radius decreases, the change in pressure increases, which means the energy increases. So we can get rid of that and that. Because although C is increasing, it is, flattening out. But we should see with time, a decrease in your radius. Oh, and because the radius is to the fourth power, that's why it'll be this one rather than this one.
Yeah, but
Yeah.
so C, why is C wrong again?
Oh, so C initially seems to be going up, right? But then it like plateaus, like it stops doing that, right? But we should see. Okay, let's see what they did here. Um, Wait, go up. I want to see where they get the like energy term from. Energy using pressure as a surrogate for energy and okay. So, in Bernoulli's equation,
What about it?
tell me what it is.
P plus concentration mass, but with volume. I mean density multiplied, I think.
So we know that these are energy values, right?
Hmm.
And if we are adding or subtracting things, they must have the same units, right?
Hmm.
So pressure, since we're adding that, can be used as a proxy for energy, right?
Okay. Wait,
Yeah.
why?
Because of these terms, right? Like for instance, let's say you had like 1 kilogram plus 1 Newton.
Hmm.
Could you do that?
No.
Yeah. Because if you're adding or subtracting values, they must have the same units, right?
Hmm. So
So,
pressure equals energy here.
yeah, it's like not really. Like technically, it's what I wrote before, like PV, right? Because let's think about it, right? Pressure is what units? Like, you know.
Newtons per meter squared or pascals.
So now we multiply that. So what would the unit for volume be?
Meters cubed.
So when you multiply these, what do you get?
N over M.
Try again.
Oh, N times M.
Which is energy, right?
Yeah.
So we can agree that P times V is energy,
Mhm.
right? So over here, do you remember how this is just like mv squared plus mg squared? Like, how do we go from the mv and mgh to the rows?
We multiplied by, I guess, 1 over V.
So you're saying divide by volume,
Yeah.
right? Now, if we had P delta V and we divide everything by volume, you'll get your rows and P delta V divided by V,
V.
your P.
No. Still tricky though.
Yes.
Very.
Yeah. When I was reading this, I was like, how, like, I thought they were going to be more like, what's the change in continuity? Yeah, I thought they were going to ask something like that. But, but yeah, the energy part, I was spending some time thinking about. And then I remembered there's PV work, right? And if your work is equal to P delta V, the work is proportional to the pressure. So I can use pressure for energy. But in the Bernoulli equation, it's even better because then you can see, like, because if you've ever, like, that it's conservation of energy applied volumetrically, but what's up with that p-value, right? Like, that's typically not in conservation of energy, which is typically this. But if you think about it, this would work for energy, but if we're dividing it by volume, that volume term leaves. So so yeah. So I knew um that the change in pressure from the Poiseuille's equation is inversely proportional to the radius to the fourth power, right?
Mhm.
And so I knew that, and then they said over time the radius decreases. So over time, the delta P should increase, right?
Mhm.
And the delta P we use to as a proxy for energy. So over time, we should see the energy increase. So that's why I got rid of A, right? And then I got
Crazy.
rid of C as well. And then it's a matter of if it's a linear increase or a parabolic increase. And since it's r radius to the fourth power, it's exponential, so it'll be an exponential curve pointing like that.
Which experimental approach can be used to analyze the metal content of soapy precipitate produced by reaction 1? Dissolve the solid in a known volume of.
Okay.
Metal content of soapy precipitate produced. Metal content. Reaction 1. Okay. No clue really. I would think that it wouldn't be C or D. I don't know. This
Okay, let's
is
see. Soapy precipitate means, it's, this thing here. And we want to dissolve it in something. So, like, this can be dissolved. I mean, it is dissolved because it's aqueous, right?
yeah.
This precipitate is not dissolved. That's why it's solid. So, we want to see if maybe we can go that way, right? And
Hmm.
so we know that this one is when it behaves as a base, right? And this one is when it behaves as wait, yeah, the base here, and well, this isn't going to be an acid really, but hold on, let me see. So dissolve the solid in a known volume of, let's see, I'm gonna look at the first part of the choices, and I'm gonna kind of go that way. So if we added this, it would just turn into the bicarbonate um ion, right?
Hmm.
Which will be like a base, like a weak base. Um, NaOH, which will be a strong base. NaCl, which will just be Na plus Cl minus, and that might play a role in like the common ion effect. And then HCl, which is of course, uh, an acid. Okay, so now if we had our C17H32O CO2 2 minus, um, and okay, we want to get to that point. So we want the M, the metal content. And when they say metal content, I mean like technically the sodium is metal, but maybe they mean the capital M. I'll take that to mean it's a capital M. So we want to, let's see, turn it back into a base. If you want to turn something into a base, you want to um let's see. Both of these are bases. This is just spectator, and this is an acid. So, I'm just gonna kind of somewhat guess here, but I'm gonna lean towards either these two just because A and B both involve adding bases at first. And now I'm just going to look at the second part. So titrate with standardized. Okay, so this one is titrating with standardized, like whatever, strong acid essentially. This is also strong acid. And then these are bases. Hmm. Titrate with standardized base using an indicator. Okay. Hmm. Mm, okay, the bottom one, or C and D both talk about adding sodium hydroxide, and oh, and then these are titrations, which typically involve acid base acid titrations. So this one is not gonna really be a it would have to be an acid to be titrated by the sodium hydroxide. So my D, I'm leaning maybe towards D, but I honestly can't really like answer it directly because I'm understanding what. Okay, got it. Let's see. HCl will generate the free fatty acid. Free fatty acid. Addition of HCl. Soapy precipitate is a salt of a weak base. Generate free fatty acid that could be neutralized by that. Difference in the number of moles reaching the endpoint. Much better dissolving the precipitate in an acid. We increase solubility. Well, you see this part? Since we're titrating an acidic thing, we must titrate it with a base. So yeah, like I can't honestly tell you like how to answer this directly. Like I understand that we're trying to get to this point from here, but like I'm trying to think, okay, how can I get this M out? And I really just saw like the first two choices, were bases. The next one, spectator. One after that's acid. And then from there, I know that if you do a titration with like a base, you would need the analyte to be an acid. So that ruled out C. And yeah, I think that's, yeah.
Got it. Okay. All right. I think that's it for today.
Yep.
So tomorrow I'm taking Altius full length 4.
Okay.
We'll update you on that as always. And yeah, that's really it. I mean, I'm hoping I've gotten 128 count the previous, like 2 weeks ago.
Yeah.
Well, and then last week I got 128 biological count. I'm praying that I can put it together, one of these next couple weeks.
Yeah. Yeah. So, as long as you're scoring in that region, we're good. So yeah, good luck tomorrow. Today it should be 120.
Okay.
And yeah, okay. So yeah, good luck tomorrow.
Well, yeah. Thank you so much. Bye.